Starting again, the next session, we were talking about the Reynolds number. It's inertial forces divided by viscous forces. So it will lead to this formula where you already explained. Vd is the drag velocity, L is the characteristic length, and is the viscosity, and D is the rho is the density. So if the Reynolds number is less than 2100 or 2300, there will be laminar flow in the microfluidics. And if the Reynolds number is greater than 4000, turbulent flow. So high and low Reynolds number splits. When Reynolds number is low, viscous interaction between the wall and fluid will strong, and there will be no turbulence or vortices. So you can see for laminar case, this there is just coming here and then straightway passing through the outlet. But in turbulent case, fluid is coming from here and it's making just a backflow like this. It makes some vortices or some rotation and flow. So you can experimentally, these are the some images for Reynolds number 1, 10, 26, 41. You can see, and even for 2000, here you can see there is very rotation in the flow that is turbulent, and all these are related to the laminar flow. So coming to the hydraulic diameter, DH. That is very important term. Hydraulic diameter is basically the fluid portion of the channel. For example, we are talking about some pipes, and the flow is passing through that pipe. So the outer steel structure or plastic structure is not part of the hydraulic diameter. The inside fluid portion is called hydraulic diameter. And that diameter is, in case of circle, dH is equal to D. And in case of analysis, that will be dH is equal to D minus D. Small d is for just an inner diameter. In case of rectangular shape, it will be 2AB plus AB. Similarly, for other shapes also, it is presented in the slide. Just for one case, I will uh, make it just like we have this kind of channel that is rectangular times, just like this, and fluid is coming from here and getting from here. So uh, this is X, this is Y, or you can also say it A and B. So basically, hydraulic diameter DH in this case is 2AB divided by A plus B. The A and B are just the dimensions, this and this dimension. So you can see, we can easily do the calculation. For example, someone gave you the pressure drop, length and viscosity, everything. So you can easily calculate the Reynolds number, and then based on the Reynolds number, decide that the flow is either laminar, transient or turbulent. And then accordingly, you can apply the basics to the for solving your problem. Related mixing, that is interesting topic, and maybe I will conduct some workshop and some seminar on that later. Even I have command on it, and during my MS and PhD, I worked on microfluidics mixing for point of care or lab chip devices. So you can the concept of mixing is if two fluids are coming to the channel. So you can see for cycle 1 and cycle 2 and cycle 3, they have mixed two fluids. So microchannel related, there may be circular tube, rhombus, some different shape, trapezoidal. Depending on your application capability, you can make any shape geometry. For example, human circulatory system. So there is definitely arterial system and there is venous system. The one for deoxygenated blood and the one for oxygenated blood that is circulating. So through veins, the deoxygenated blood is going, and through artery, the oxygenated blood is going. Except one artery and one vein, that is pulmonary vein, and that works for opposite cases, means for oxygenated and deoxygenated. So these arteries or veins can also be studied in simulation and through microfluidics approach, because some of the veins are very small in size. So based on the heart problem, based on the veins problems, you can also use microfluidics approaches. So this replication is in biomedical engineering. Related skill, and skill there are very small minor veins. You can apply the same concept. As I mentioned, there are some other numbers, just like a constant number and some other things. We will skip that. There is also another important basic principle for microfluidics, that is diffusion and fluids. So for diffusion, the formula is x is equal to under root 2 dt, or you can write tau is equal to 1 over 2 x square divided by d. D is the diffusion constant. For example, in console, if you open it, there is mentioned 1 into e power 10 power minus 9. That is by default the diffusion. But the diffusion value is dependent on the two fluids that to be mixed or that to be used for any purpose. So the diffusion values may be vary, sometimes at 10 power 9, sometimes at 10 power 10. And x is the diffusion length through which the fluid is well diffused, and tau is the diffusion rate. So laminar flow limits benefits for fluid mixing. Highly predictable diffusion has enabled new class of microfluidics mixture. So definitely, with straight channels, there will be only diffusion. There is one law, Fick's law. Fick's law of diffusion deals such kind of problems. So these were all the basics. Summary is here. I'm not going to repeat it, but here you can see these are different Reynolds numbers, dimension number, dimensionless number, just like Reynolds number, Picklin number, Weber number, Thomson number. Its formula, its definition is in front of you. So these were the basics for the microfluidics. Because when we are going from the macro scale to micro or nano scales, the laws that are applicable for macro scale is not always valid for the micro scale. And even the some of the laws for micro scale is not valid for the macro scale. Because at smaller level, we sometimes ignore the surface tension and such kind of things. But at macro scale, we cannot do that. And sometimes, so these were important to study. Now coming back to our original slides again, microfluidics and mechatronics, it will lead to the miniaturized fluid control system, lab and chip integration, a sub-robotic application, and embedded sensor and actuators. So, mechatronics, fluid control system, miniaturized system, I already explained that when the different sensor will be integrated in the system, that is called miniaturized one, you can utilize the concept of microfluidics. How about the lab on chip integration? Lab on chip is a concept that you are considering all the reaction or all the phenomena on a single chip. Just like there is some laboratory, some different works are going on in it. So you convert all these reaction or all these activity to a single chip. This is called lab on chip integration. So you can also use it for lab and chip integrations. You can use for soft robotics applications, just like the word is going from the hard robotics to soft robotics. Soft robotics is very important area of research nowadays, and its implications are very deeper. Then soft robotics, just like Prague-inspired or laser-inspired robots are developing, and I saw many papers on it. So the purpose of soft robot is it can squeeze through narrow area, and it easily can move from one place to another place. Similarly, it will not be easily damaged because it's soft, so it will be squeezed and then regain its original position again. But in case of hard robotics, it's difficult. As in the third point is in case of soft robotics, if it is made of elastomers or any ecoplast, it will be it cannot damage our human body, but some equipment of the laboratory. But in case of hard robots, what will happen? It can damage the equipment. It can also it can also make problems for humans because sometimes if the boat runs in the wrong direction, I have so many videos. The robot is dangerous for human. So some robotics is another field. Microfluidics can be applied to it. Embedded sensor and actuators. Sensor and actuators are very important for any type of devices. So we can also utilize the microfluidics approaches for that. For biomedical cases, just like I mentioned, that we can use this approach for point of care devices. For example, sugar testing device or some other devices. The idea is it will be portable. It can be easily moved from one place to another place. For example, someone is very ill and we cannot move it to the hospital. We can easily just bring that device and we can make all its tests easily. Organ on a chip model. Organ on a chip is a new hot topic. top 10 topics. I also worked on it in the during my PhD, and I contributed in the projects. So organoleptic concept is just like there was one scientist, Egbert. He also awarded Nobel Prize on it. He published his first paper in the Nature. I will show that paper as well. He replicated lung on the chip, lung on the chip. Lung on the chip concept is definitely cannot replicate the human body on the chip, but the idea is they are planning that they are replicating the human organ on the chip. Just like uh, they have fabricated some channels and they have applied some vacuum and the membrane is pushing and it's working like a lungs and its functionality is just like a lung. Although it will not, definitely it will not lead to exact replication, but to some extent they have replicated the lung on the chip. Similarly, they have replicated kidney on the chip. On the chip. The idea behind that is, and the history, there were models that medicine was tested on mice and some other animals. And when that medicine was applied to the human, it was not equally applicable, and its response was different. So the history about organ on a chip is, the idea is they have to replicate the human object or human body or human organ on the chip, and then they have passed the fluid and test the drug. And after that tested drug is verified, it should be applied to the real-time human. So that will lead to real-time and good medicine at the end, and it will equally applicable because human body response is different as compared to the animal body. So the goal of organ on a chip model is they are planning for individual organs, and at the end they will replicate the complete human body on the chip. So a very tiny, just like this size chip, the complete human body will be replicated, not in terms of physical shape, but in terms of its functionality. So that is the future goal of, and they are working on it. I will also show you some of the paper I have downloaded, and you can also search some more paper on it. Drug delivery system, definitely, we can insert the drug directly through mouth. We can insert through the veins, and we can also use some different techniques. So drug delivery, microfluidics approaches can also be used for drug delivery systems. You can make some surgical reports, something like that, and you can easily implement the concept of microfluidics for making compact size shapes devices. Cell sorting and analysis. Cell sorting means separation of the cells based on the size. So you can also do that through the microfluidics. It is also very good research. And regarding organ on a chip, uh, it's not just limited to the making the channel and passing the fluid through it to make dynamic environment. We also take cells from the human and we culture that cells and we put it at the central chamber of the microchannel, and we then check its response. Previously, that one limitation was that tested the human mice animals and then use the same medicine for the human. The second limitation was they used human cells and the straightforward channel and a container or in a beaker. So in human body, the blood is circulating and that make dynamic environment. But you studied it in a stationary environment. So when you make the medicine, that is not equally applicable. These two limitation removal, they have worked on the organ chip part. Organ chip is also part of lab on chip technology, but lab on chip is just to replicate the laboratory functions, and organ chip is to replicate the human functionality on the chip. So there is again biomedical application and DNA and protein analysis. So this DNA analysis, deoxyribonucleic acid, and protein analysis. For that purpose, you can also use microfluidics approaches. How we can intersect the Mechatronics and Biomedical through microfluidics approaches. Variable health monitor with microfluidics suite analysis. So suite detection and suite analysis, we have also published one paper related to it. We have fabricated some microfluidic chip, and then that variable means just you can insert it on the human body and it will detect the suite, and from suite contents, they will tell you that you have tuberculosis or not. So that is equally applicable, and that is only possible through mechatronics or mechanical approaches to fabricate the variable device, and then it will apply to the biomedical problem for detection purpose. Automated infusion system with feedback control microfluidic pump. You can also use it by microfluidic pumps, and that microfluidic pumps can be equally used for mechatronics and biomedical applications. Surgical tools with microfluidic assisted drug delivery or suction control. You can also use microfluidics for making the suction control or drug delivery systems. So, just coming to the papers related to this topic, I will. This is emergence of microfluidics for next generation biomedical devices. This paper is published in 2022. Uh, Here you can see they have started from where the microfluidics application and everything started. Soft lithography is the technique for fabricating microfluidics devices, and nanoparticle generation and its implementation can be used for biomedical devices. So nanoparticle and its flow can also be studied through only microfluidic approaches. So drug carrier, Parleba chip devices, micro needle, and drug delivery system. We know we are familiar that some patients are using two or three times injection on daily basis. So the large microneedle is very painful for them. So using the microfluidic approach, you can create some small chips, and that will be very comfortable and easy, and even the patient will insert it by themselves for drug delivery. Okay, so that is also possible. That is fabrication technique. I'm not going to its detail. You can see this is the channel through which the fluid will flow, and this is the microfluidic portions that can be used for different uh, biomedical devices related. So I was talking about this concept. This was some Egbert scientists. You can see here and here. These are the vacuum pump, and this is the membrane. And this membrane you can see stretches, and these stretches just replicate the. You can see here the cells are from the human body. Epithelium cells are cultured, and vacuum pump is applied by pushing it. And it works like a human lungs. You can see so mechanical stresses can create such kind of environment. For the first time, this was done by Ingvar, and he was awarded with Nobel Prize. This was the starting point, and maybe uh, it's proceeded to, you can see proximal tubule on the chip and the kidney on the chip. And ultimately, you can see that they are focusing on the body on the chip at the end. Okay. So these are the different companies. You can see these companies are working on different application, for example, protein cases, nucleic acid cases, and these are the related papers. So you mentioned that organ on a chip was introduced by Donald Egbar. This is the scientist, okay? So he for the first time did published in Nature this paper. This was the epithelial cell, and through cells the fluid was passed, and you can see this was the model, and these are the detail of the channel, and this is the microscopic images of the cell culture inside the microchamber, and you can see this cyclic strain. We provided cyclic strain at these two portions, and this was only 100 micrometer channel. Okay, and you can see this was the cell culturing reports. So he created the same environment just like in the human body. That is why he was awarded for this work, and also this published in Nature. Nature is very high impact journal. You can see it from the Google. So uh, it's all about from my side. If there is any question, then you can ask.